Very good afternoon to all of you. It's a great pleasure for me to introduce our today's speaker, who is going to talk to us about various aspects of DSP application. This is a subject actually in which we should all be deeply interested. Our today's guest speaker is Dr. N.M. Biradar, Principal, BKIT Bhalki. He has completed his PhD from IIT Roorkee in the area of biomedical image processing. His area of interest includes DSP, image processing, and biomedical image processing. He has more than 20 plus publication in different SCI and Scopus Index journals and having teaching experience of more than 20 plus years. I request you, sir, to take a charge. Over to you.
Thank you, sir. Thank you for this opportunity. I, on my personal behalf, right, would like to thank Power Madam, Matpati sir, all faculty members having made me to prepare and talk to the students. I've bbeen talking to students after a long gap now, right? I'm
Yes, sir.
yeah, I'm talking after a very long time, right? But still, I'll try to be very brief and I'll not get. I hope that I'm only talking to students. Yes, sir.
Yes, sir. Or third year students.
Okay, fine, sir. Therefore, I'll keep things very simple. I'll not.
Sure.
Right, and I'll be. What, sir? Allotted time for me is 45 minutes, 1 hour.
No, so actually you can exceed up to 2 hours also.
Okay. I know, but I have to rush to a meeting. It's all right. Okay. Right.
No problem, sir. As per your convenience.
Yeah. Thank you. Good afternoon, all. Right. I begin with this particular saying, sharing is good. And with this, we are into digital technology. Sharing is easy. That's why I, sitting at Bhalki, is talking to all wonderful students at Pandharpur. Right. So we begin with this. Let us try to share the information. The topic given to me.
Sorry to interrupt you, sir. Will you just make a full screen, full view PPT?
Okay. My audio is all right?
Yes. Now perfect, sir. No problem.
Okay. Thank you. Audio is all right, right?
There is some disturbance in audio.
From my side, there is nothing adjacent to me. Okay.
Okay, no problem, sir. We'll see.
Okay. Right, we all know digital signal processing is used everywhere now. You find its applications in your audio signals, speech signals, your radar signals, image processing, audio processing, sonars, right? That's a part of your radar again, voice recognition, speech recognition, handwriting recognition. You name an application, probably there is nothing called where you do not find an application of DSP. For example, DSP is being used for speech compression and transmission for mobile phone. Probably most of the students have logged in using their mobile. And you know that the data, once you upload the data, it's of a large size. But what happens is when you try to download, right, the data gets compressed and you have maybe in terms of megabytes, you uploaded the data, but it's coming down with a smaller value. It's being used in your headsets to protect users' hearing damage. Right? Normally, what happens is you're not listening now, probably you're using your earpiece or you're using your headphones. If current passes through these headphones, probably your ears will get damaged. Therefore, it's important that the equipment which you are using, whether it's an earpiece you're using or it's your headset you're using, all these, right, the signal that's coming through the wires, whether it's wired or unwired, it has to be processed. So what we do is suppression and enhancement are equally important in this particular case. You know that suppression, I mean, if it's very large, probably you should be told that the volume you have kept is large, therefore it should be reduced. If it is small, right, then probably it should say enhancement is required. Then your other applications would require your MP3 file manipulations, audio signals, which you, right, these days, right, a lot of mixing takes place. Old songs are mixed with new songs, or audio of somebody is being mixed with the audio of somebody else. Therefore, your manipulations are plenty. But it's not just to all these, right? This is your DSP finds a lot of applications with respect to medical, where myself and Power Madam had worked, right? So there are a lot of applications where we use DSP, right? Your computer graphics, you have a graphic card being embedded with your maybe i6 computers or higher version of that, right? All these have DSP applications. Then you have MRI scans, CT scans, ultrasound, echocardiography, EEG, ECG, you name, EMG, in all these cases, right? DSP plays a very, very vital role. So for it important that we understand some of its applications could be beyond the scope, right? For me to talk of all these, I'll try to be very precise and I'll talk one or two applications, right? Then the electrical appliances which use, musical appliances, not electrical appliances, the musical instruments which use, like your guitar and others, all these cases also, right? A lot of signal processing. You'll find a lot of applications of your DSP. So, what is that then? Right? A signal, right? Signal is information. Then what's a digital signal? A digital signal is a representation of information as a sequence of discrete, finite values. These are very important words. Probably being in your fifth semester, you have studied your signals and systems in your fourth semester, I believe. Probably each one of you understands what I mean by discrete. What is the audio signal, the signal which you are receiving now, it's in a continuous form, right? You employ steps like sampling, quantization, encoding, and filtering, error correction, all these, using these, right, you convert a continuous signal into discrete signal. What it means is, for a particular point of time, for each of your sample has a definite value. Then we normally have two states. When I'm talking of a discrete signal or a digital signal, there is a difference between a discrete signal and digital signal, definitely. A discrete signal can have variation in amplitudes, whereas a digital signal is normally having two forms, 0 and 1. Therefore, a digital signal you can relate to a hard disk, which stores your information. The hard disk that stores information in binary form, and the information stored in it can be shared and processed by all who access it, right? Your pen drive, for example, right? What you do is you send your data in this, right? The data is being stored in the form of binary. When you access it, probably none of us realize how it's being stored. The data is in binary form. The conversion in binary form and storing it, it's all digital signal processing. Then what is this? What I mean by signal processing, right? The question is what we mean by processing of a signal. As I said a while ago, right? Any signal that carries information is a signal. Anything that carries information carrying mechanism is called as a signal. Any physical quantity that changes with time or pressure or temperature is a signal. The characteristic of any signal, for that matter, you take a sinusoidal signal, then you'll be talking of amplitude, right? Frequency, phase. Probably in most of your signal processing, I would not have spoken of shape. I mentioned shape because on application of your various steps, right, probably you'll be shaping your signal also. Therefore, I have quoted shape also. Any process that alters these characteristics of a signal is called as signal processing. So what is signal processing? Either you are changing the amplitude, or you are changing the phase, or you are changing the frequency component, or you are changing the phase component. But please remember what all changes you do, right, at the end, right? The information, the signal that's being sent has to be restored back at the receiving end. We process so that maybe the error component is being removed, the noise component is being removed, the clutter that's being introduced is removed, or enhance the signal. Right? Maybe the shape of the signal is not all right, right? Because of noise, it has overshot or undershot, then probably you are boosting it. However, Noise is also a signal, but it interferes with your main signal and it impacts the quality. Mainly, it's distorting your main signal. So noise is an unwanted signal. Somebody would ask me, sir, is noise a signal? Definitely, noise is also a signal, but it's not an wanted signal. It depends on what it is. It depends on where what becomes unwanted is the definition which each one of us can have. All natural activity is considered as data in signal processing, right? For example, your images, audio to seismic vibrations, and everything that's in between is your data. Therefore, data processing it is also there. Therefore, signal processing will play a very important role. That's basically converting your analog signal to digital signal or vice versa, and your digital data to a form where human being can understand. Basically, you cannot understand if your data or information or your signal is in the form of zeros and ones. It has to be a signal where a mechanical signal, right, where voice, for example, right, you convert them into zeros and ones. If I send and ask you to decode, probably none of us will be able to understand that. Therefore, it's important that we are able to process it properly, right? That's one. And is the digital signal processing is also used for storing of digital data and streaming or transmitting of data. For example, now I'm talking, right? I'm sitting at Balki and the information is being passed to you, right, in the form of Zoom meeting. We are into a classroom. I will be speaking of the problems we'll have once we are sitting in a classroom. A while back, your teacher said, sir, there is some disturbance in the voice which is being sent to you or the voice which is being received. I said, there is no disturbance. Therefore, the challenge for digital signal processing would be, can we take out all this noise? Can we take out the clutter being introduced? Therefore, DSP plays very, very important role. DSP involves, right, basically information interchange so that the data can be analyzed, observed, transformed into a separate form of signal. Right? So what happens is, right, your DSP helps in analyzing your signal. Your analysis can be either in time domain, or it can be in frequency domain, or it can be time frequency domain. Right? You'll be using your transforms, maybe Fourier transforms or DFT or FFT. FFT is the fastest form which will take the minimum number of your gates, right? Probably you'll go for that, right? Observation, right? What is that information you are doing, right? You'll observe and transform it into a signal which is required for you. If it record noise, share it and send it. For the fundamentals of your digital signal processing, basically, we all know, right? Most of your signals, the natural signals are all analog signals. The example which I'm quoting here is temperature, voice, audio, video, pressure. It all needs to be digitized and they have to be manipulated, right, for storage and better quality. We cannot store temperature as it is, 25 degrees. But how do you store it, right? Voice signal you need to have, right? You'll be listening to music, voice, right? How do you do it? Audio, video, right? All this. So during your digital signal processing, the signals are processed, right, for the information they need to carry, and so that they can be easily stored, used, displayed, propagated, and converted into human usage. Therefore, this is what it happens. What is that? One is for storage, right? The second one is your display, propagation, and transmission. Then when you're processing your signal, right, let it be any application for that matter, whether it's your audio application, whether it's your radar application, whether it's your telecommunication application, probably these are the topics which you have. DSP applications for telecommunication, DSP application for audio processing, DSP application for others, right? Therefore, some of the key focus, right, is right. Some of the key focus are, one is speed of conversion. Right? What is the rate at which you convert the information? That's one. Ease of access. Right? You said you'll be storing your data in your hard disk. How easily are you able to access that? Security. Right? I'm talking now. Right? That information transmitted and received is secure or not. That's also a concern. Reliability. The information from where you receive. These days, right, there is a huge cry on your Facebooks, right? Probably your teachers will appreciate, right? The names, right? Maybe the login, right? On your Facebook is being hacked and people are asking for money using somebody else's address. They'll give you a phone number and they ask you to pay through, right? Maybe some phone, right? Paytm or some other account they give and they do it. Therefore, is a concern and reliably. How reliable is the information shared on the Facebook, right? How secure is the information shared on your Facebook, right? Therefore, the ease of access, all these are more important parameters that you're processing, right? While you process your signals, these are the 4 parameters. Then the major steps or more core steps of your digital signal processing is your digitizing your data, that's converting a continuous signal into a finite signal, then eliminating noise, that's the second one. Remember, with plenty noise, probably will very easily remove it. If you do not know the source, and eliminating a noise from your signal, right? If it's a multiplicative noise, for example, spectral noise is a multiplicative noise. The ultrasound machines will have this spectral noise. How can we take it out? Y is equal to x into n. Therefore, it's difficult to take out y is equal to x and n, separate x and n. You do not know what's the quantity of x, what is the quantity of n. If you look at your B mode ultrasound image, probably you'll not make a distinction between what is, in one case, your speckle will convey some information to you. In other case, speckle is treated as noise. How do we make this particular judgment? For eliminating unwanted noise, right, is one very important aspect of your digital signal processing. The next one is improving quality, increasing or decreasing certain signal amplitudes. Right? Remember, your ECG signals, your EEG signals are of very small values. They are few hertz. Therefore, if your noise is also in the same, right? Noise also lies in the same. Therefore, improving the quality. Therefore, you'll have to improve the quality of these signals. Probably, we should be able to separate them properly. Then, as I said, ensuring security, right? Minimizing errors while either transmission or detection. And finally, storage of information is a challenge, right? Probably your big data analysis, right? These days, big data is a word where everyone talks of big data. What is that? Right? But talking of information that's being that's being scanned, stored at a hospital. How long can you go? Right? You go to a doctor, right? You have some medical complications, you go to him. He recommends you certain medicines, he recommends you certain things. All these have to be digitized. When you visit your doctor next time, right? When you visit your doctor next time, the information should be, right, safely retrieved. And next time, right, what only is the medicine being prescribed, the progress of your disease, right? All that can be analyzed. Therefore, these are very important steps, right? Ease and secure of access to stored information. One is storing information, right? How well, right? How best you can store the information. That's the one. Second is, right, how easily you can store this particular information. Right? What is this, right? You in a parking lane, right? If you arrange your vehicles, if you park your vehicles, right, you can accommodate more number of vehicles, and also very easily, right? A vehicle can be parked in, or somebody wants to go back, he can take his vehicle and go back. If you park haphazardly, and what happens? Either park your vehicle, the next fellow who comes, either he can park your vehicle, nor somebody who has already parked his vehicle can take it off. Therefore, that difficulty will be there. Next, right, as I said, I'll not get much into this, right? Early in your already, most of the syllabus would have been completed to you. Right? We are into second month of since the college has started. Probably your concerned teacher would have spoken regarding these sampling, quantization, errors, and filtering. Right? I have a question. If somebody can tell me, right, what do we mean by sampling? Can anyone answer? Let us make it interactive. Can anyone tell me what is sampling? So can we have this facility? Can we discuss?
Yes, sir. You can.
Can
Students
any
are
student?
listening.
Yeah. Some student can tell me what is sampling, because I see a lot of them. Else probably afternoon after lunch, probably people will go to sleep. Any answers, please? Yeah. If somebody raises his hand, he can give a chance. Else I'll continue. Anybody,
Okay.
please? Anyone? What is sampling? How do you? I'll not go to this. Yeah. Sampling, please.
So you have studied the sampling theorem, right? So you can answer this question.
I'm asking a question because, right, I know I have limited time, but still I'm asking only to make you, right, everybody should listen to me. That's all. Any answers, please?
Saili, Madhura, you can. Mahesh.
Yeah, somebody. Yes, sir, please.
Hello,
Yes,
sir.
sir.
Yes, please. What
Please
is
answer
sampling?
the question.
Sampling is a process used in a statistical analysis or representative samples.
Please. Can anyone tell me the sampling theorem statement? Because anyway, in 4th sem you have studied, also you have studied in 5th sem. What does your sampling theorem state? Yes, please.
Sampling is convert analog signal into digital signal.
Yes, please. Good. Can anybody tell me? Please repeat.
It converts analog signal into digital.
Then A to D, then analog to digital converter it is. But what is sampling, I'm asking? What does your sampling theorem state? This is important, therefore, that's why I'm asking you. Because next few of my slides will have to. Yes, please. Yes, dear, please.
Minimum sampling rate at continuous time signal.
Okay. Can you refine it, please? Can you refine it? It's good, right? Can you refine further?
Minimum sampling rate at continuous time signal. Uniform get cast the word.
Okay. Any other answers among 76? There are, including me, 76. Any other answers, please?
The sampling
Sir is
theorem
asking about
specifies
relationship between FS and FM.
FS and FM. Can you tell me what is that? FS and FM? FS should be more or
FS
FM
is
should
greater than or equal to twice FM.
Very good. Can you put them in words now? Very good. Can you put them in words?
Sampling frequency should be greater than or equal to maximum frequency, twice of maximum frequency.
Very good. Okay. Right. But what I wanted from all this discussion was this. A band limited signal can be converted into samples and also reconstructed back if and only if Fs is greater than or equal to 2 times of Fm. This is your sampling, right? If Fs greater than 2 times of Fm is your Nyquist rate, right? That's called as Nyquist rate. Therefore, what is sampling? It's basically a process of converting a continuous signal into its samples. But how do you do this? Right? Therefore, it says the first condition is you'll have to make that signal band limited. If you don't make the signal band limited, what all is your FS you're calculating will go wrong and your entire process will be under problem. Therefore, it's important to make a signal band limited. Therefore, what do I mean by band limited? If you're defining your signal is from 10 hertz to 15 kilohertz, right? 10 hertz to just 15 hertz. Therefore, your signal should be between only that. But what happens is if you do not make your band limited, therefore your signal can start from 9 and it can go to 16. Therefore, then it becomes a problem. Then it would be a problem. Therefore, please understand that sampling is a process where the basic requirement is you'll have to make band limited. How do you do this? Really, each one of you studied. How do you make signal band limited? Any answers, please, for this? Have you heard of a pre-alias low-pass filter?
Using band stop filter.
Band stop, not band stop. Sorry, you'll have to use a low-pass filter. Okay, right? Because noise is a very small value. Use a low-pass filter, then subject your signal to sampling. Ensure that Fs is greater than 2 times of Ff. Then what is aliasing, please? Any answers? You can answer this. Right? I know that most of you know this. What is aliasing? Yes, please. Hurry up, hurry up, hurry up. Aliasing? Anybody in the class, please? I'm asking a literal meaning, right? I know that you'll say when Fs is less than Fm, you'll have this problem, right? Yes,
undersampling.
What do you mean by aliasing? Aliasing. Aliasing का मतलब क्या है? मुझे मराठी नहीं आता है, पर aliasing के मतलब क्या बताइए? Good. Please. Yes, please. Somebody was telling, please hurry up. Okay, right? Aliasing, right? Basically, in technical terms, in a general meaning is, right? Somebody representing somebody else. What I mean by that is, probably a student of class 10 comes to your class, 5th semester class, and says, I'm a student of BE 5th sem or BTech 5th sem. Or you go to, right, you students of BTech 5th sem of ECE, you can say that I'm a student of BTech 1st sem. Right? Therefore, in those two cases, your higher frequency component representing themselves as lower frequency component is aliasing. I repeat, higher frequency component representing themselves as lower frequency component is aliasing. What happens is, the process is, you'll find that the spectrum overlaps one or the other. Okay. I'll proceed now, right? Have uniform sampling, I'll not get into all that stuff now, right? Similarly, sampling is a process where you're converting a continuous signal into its samples in discrete one. And we have a process called as quantization. You all know that you want to, your continuous signal has multiple amplitudes. Therefore, time domain you have made discrete, but in amplitude domain, still there are values for you to write in terms of zeros and ones. What you do is really, you'll all slash them up, right? You maybe the tops is being cut off and you bring them to one particular level. Fellows who are values which are greater than a particular value, you cut them. The lower values are being pulled up, right? And you bring them to one particular level, right? Then to do this, really, you'll use uniform quantization, non-uniform quantization, all that. And errors and filters. I'll come to these two. As I said, sampling is an approach to convert your analog signal into time discrete form by sampling its value in a periodical intervals called as your sampling period. The amplitude value of the signal is measured at a certain intervals in time. The sampling rate is the number of samples or data points within a second. It is also referred to as samples per second. Can anyone tell me, how are we able to do this? Right? How are we able to do this and why are we doing this? Any answers? Anybody, any answers for this? Why do we, right? You're taking two nearest points and you do it. How do you decide on these two nearest points? Right? What is being done is you have redundant information. You want to take out redundancy. If two samples are conveying same information to you, then what's the point in sending two of them? You send one. That's how we do it, right? Redundancy is being taken off and we ensure that discrete, very finite values of these samples are being transmitted. Samples enable higher frequency handling. Right? Quantization, I already said, right? You are bringing them to one particular value. I'll not get into this. The next very important is the errors. I already spoke of aliasing, right? Noise, as I already said, disturbance, right? Or modification in useful data, right? That's being occurred because of some reason, right? It can be because of the environment. You all know across the channel, right? Some noise may be induced, or right when we are transmitting, I'm talking about, right? Maybe I take my pen and hit it. Therefore, this is a noise. This is a noise. What I'm doing is I'm taking a pen and making. This is unwanted, right? Therefore, this is man-made. But there can be something where probably, right? I'm sitting in my chamber, right? If there is some noise, some other noise, electrical noise and others, that will be natural noises. Therefore, it's important for us to take out these particular noise. The next one is aliasing, right? When you are converting digital to analog or analog to digital, right, your unwanted components are detected, right, while you reconstruct. This phenomenon during the reconversion process, right, of digital to analog signal, sometimes a few unwanted components are detected in the reconstructed. This phenomenon is called as aliasing. This is how you'll find the information in that. This occurs mainly because of overlapping of signal frequencies. Lower frequencies. What happens is your higher frequency component will come down and sit on the higher frequency component. Your lower component can sit on higher can sit on your lower. That's the problem. The next one is the next error is the jitter. And this is basically delay in transmission and reception. What it will do is if there is a jitter, I'm talking now, right? If my audio is being delayed, right? Each word or each symbol I'm talking now, if it gets delayed, then it's a problem. You all know, right? Most of you probably watch these live matches, live cricket match or kabaddi match or T20 matches. You all observe. There's some problem, right? With respect to the those who are broadcasting. They said we'll send the programs will be telecasted 10 minutes delay from actually what happened. Then the revenue came down drastically. I do not know how many of you appreciate this particular example. If you are somebody, a football lover or cricket lover, probably you'll know the importance, right? A match between India and Pakistan or India and Australia. If you know that your information is coming to you 10 minutes late, that is after 2 hours, right? Actually, 2 hours are over, but you're getting information of first hour then, and it's a problem. Therefore, it's a delay in the signal transmission and reception. Impact on your signal's phase, width, period, or cycle. It's called as the monitoring of delay. It has nothing to do with that particular, right? It may result in your transmission delay of few packets, then multiple packets sent together. What happens is you are not able to send all of them are being pushed at the same time, and it becomes a problem. For the next one is your filters. Probably you'll all be studying regarding your FIR filter, IR filter. You'll be talking of, you'll be studying regarding Butterworth filter, Chebyshev filter, right? Then all these filters, if you're talking in terms of low pass filters, high pass filters, band pass filters, band rejection filters, right? Well, depending on the usage, right? Whether what type of response are you looking at, whether you want a finite response or infinite impulse response, right? Different filters are being used. And all these filters, right, are being implemented in different forms. Direct form 1, direct form 2, then you have various other forms, right? Cascade form and others, right? It depends on what application you're talking of. These are part and parcel of any application, whether you talk of telecommunication, whether you talk of speech, whether you talk of audio, applications of DSP, all these filters come into picture. Low pass filters are basically being used to circumvent the aliasing error, right? Somebody said bad pass, right? You need to correct that. Low pass filter it is. Then your high pass filter are used to circumvent the noise error, right? Maybe some night sitting at a table or fan makes a noise, well, that can be taken off. Then coming to the applications now, applications using your digital signal processing, right? The best example for you, the most simplest example which I can start, right? Because to make you understand, I've taken MP3 audio player, right? Your music or audio is being recorded and the analog signals are captured, right? Being a good singer, right? Maybe singer, right? You take the examples of Lata Mangeshkar or somebody, right? You want these audios to be recorded, right? So these are basically analog signals. Analog to digital convert the signal into digital signal, and the digital processor will receive this digital signal as input, and it will process it. Remember, this information will be in the form of binary, right? The storage in the form of binary. As in when you want to play back, right? Your DSP processor will decode this stored data, and you'll have digital to analog conversion, because if you play in the digital domain, probably I and you will not be able to understand anything. Therefore, it's important that these, right, the data that's being stored, right, are being converted back. Then digital processor will improve the quality of by improving the volume, reducing noise, and also employing your equalization. One example. This is I have shown in the form of a figure. One is your recording, right? Then once you record it, this is in the form of analog. You convert them, right? Use a ADC, convert analog to digital convert. Then feed it to your DSP processor, and this information goes to memory. Then when you retrieve it, right, again you have to convert that back to digital to analog. Then your signal is in the mechanical form. Then there are various effects that probably people who are knowing regarding music, right? A lot of audio effects. Audio effects, right? These will alter the sound of a musical instrument or other audio source. Some of the common effects that are there, which needs to be addressed, and where your DSP can play a role. First one is distortion. When you use your guitar, right, in your electric blues or rock music, right, normally you have distortions being there, often used with your musical guitar, right? Most of the time you have distortion. When you're using your pedals, right, volume pedals and compressions, then there are effects on your dynamic effects. Maybe you have to very carefully adjust the volume knobs, right, and the compression knobs to have a correct impact of your loudness and pitch, right? When you're talking of an audio, right, you have your pitch, loudness, all this comes into. Then you have wah-wah pedals, right? This basically different being employed with physical instruments, right? Therefore, there will be an impact on this. Then we normally use graphical equalizers, which modify the frequency ranges. Then we have different modulation effects, might be chorus, flangers, phasers, etc., etc. Then you have pitch effects, as I said a while back. You have pitch effects such as pitch shifters, right? You want to shift it. Right now, I'm talking slowly. Probably you want to increase my pitch, right? At your level, probably you enhance it. However, for all these provisions, for all these effects, you have your DSP that comes into picture. Then you have time effects such as reverberation and delay, which creates echoing sound, right? Sometimes echoing is not good. I'm talking now. If my voice is coming back to me, then it's an echo. If I'm able to hear back when somebody is speaking and among the audience is trying to talk to me, but what's happening is I'm able to talk, receive both information. One is the speaker, other is my own voice. Then in that particular case, you'll have to have automatic echo cancellizers, right? Echo cancellation has to be introduced. Therefore, that's a problem. Therefore, time effects such as reverberations, delays, which will create your echoing sounds and emulate the sounds of different spaces. That's a problem. Therefore, musicians, audio engineers, and record producers use effects units during live performances, right? In the studio also, typically with your electric guitars, brass guitars, electronic keyboard, or electronic piano, where all use an electronic device. In all these cases, right, we'll have to use different, maybe different things with respect to reducing the impact of unwanted things, increasing the impact of wanted things. Therefore, your DSP will play an important role. Next, right, I'll not get much, you all know this, right? The computers and your laptops, right? Your latest computers, right, and your laptops, maybe i6, i7, i9, right? They're very flexible, faster, right? They give you better quality, better portability. All that's because of your application of your digital signal processing. Right? You're able to process your information. Right? That's the importance of hardware. Right? Please remember, these days, right, there is a huge demand for computer science. Everybody wants computer science. But you as electronics engineer, right, the devices, the computers, the mobiles, which you people, right, will be part and parcel. Remember, they're very, very important things. And whosoever wants to get into the hardware domain, right, probably your DSP would be one mandatory subject where you'll have to understand your filter designs, your sampling, quantization, all this stuff has to go. You have to study well with your DSP. Right? These days, right, when you purchase a laptop, right, you purchase a graphics card, right, that will convert your digital signals to analog signals and transfer them as an analog display for your better viewing. If you don't have that, probably the images are not being properly displayed. Then there is the other important thing is, right, the connectors which you have, right? There are various different connectors. You have different ports to your computer, right? You have different ports to your other electronic gadgets, right? There were different of these connectors. They offer you different services. First one is your digital visual interface integrated that puts your analog and digital signals. Digital visual interface digital, it supports only digital signals. Then you have DVIA that only supports analog. Then your HDMI, it supports digital audio and video transmission. The video graphics array, VGA cables, right, it supports analog video signals. You have coax cable, Ethernet cables, support both analog and digital audio signals. The reason I'm is because I'm talking of, right, analog, digital to analog. Therefore, you should know which particular cable or which particular port will support what type of connector. It's important to know. Therefore, this slide I put here. Then next, right, you all are using smartphone, right? Probably most of your applications in your smartphone. Your antenna, for example, antenna, right? The signals from your antenna, right, play a very, very important role. Yes, smartphone, iPads, iPods, etc. are all digital appliances that have processor that takes input from the user and converts them into digital forms, process them and displays them as an human understandable form. Then you have other electronic gadgets also. Then you have automatic electronic gadgets. I'll not get into this. The other attributes, talk of any application, right? There are certain important application requirements and processor attributes, because your processor speed would be very, very important, right? You're talking of i6 computers, i7, right? Version of that. Why are you going for that, right? The reason is we are going for multimedia applications and the requirements have gone up, right? If you're doing real-time processing, for example, ECC signal analysis, EEG signal analysis, ultrasound, right? That's being, you have a lot of scans with the doctor. All these have to be analyzed in real time. Therefore, from the processor end, you should ensure that you have high speed and high throughput. When you're talking of, and your requirement is large array of data, when you're processing, maybe at the reception, or a fellow who is browsing information, a lot of information, patient information being dumped in one computer. In this particular case, what happens is you should have, or you should have algorithms, right, which will have instructions to move and process large data arrays. Instead of 8-bit, probably a 64-bit processor or a 128-bit processor, something like that. Then there can be an application where it's algorithm intensive. In that particular case, right, you should have a faster mathematical computations. Probably you'll have to, instead of using DFT, you'll use FFT. Instead of using FIR, probably use AIR. It goes, right? All these single cycle DSP operations should be there. System flexibility, right? Your flexibility, right, should be general purpose programmability should be done. And then other important is your EPROM. What's the capacity of this? These are right, the requirements and processor attributes. Being a electronics engineer, right? Most of the computer engineers write algorithms for us. Therefore, the interface between electronics engineer and computer engineer is very important. Therefore, we should understand the hardware requirement and software requirement, and we should be able to amalgate them, integrate them, and things should be all right. The next one is your digital signal processing in its role in your communication. Right? I was told by Dr. Matpati sir saying that you have DSP applications in communication as part of your syllabus. I've put a few things here, right? You all know, right? Probably we are into a room now, right? I'm sitting at Balki. You are at various locations in Pandharpur, right? We are into a meeting now where information and people collide with one another. What happens now, right? You're right. It's good that all of you have turned off your video, turned off your audio, so that what all I'm talking now, you are able to receive it. But if everybody turns on his video, if everybody turns on his audio and starts speaking, and what will happen is you'll have a collision of information. And what happens is, right, neither the transmitter, I as a transmitter, will not be able to pass on the information which I want to do. Therefore, it's a problem. Therefore, meetings are places where, right, you have a lot of requirement and applications of your DSP. Meetings are where, right, information and your people collide. Although the technology has evolved to make it this easier to collaborate with people from all over the world, providing video and fully digital integrated presentation capabilities such as screen sharing and online collaboration. One thing still remains as essential as our experience is crystal clear audio. The teacher who was talking to me, right, who introduced me, he said that there is some disturbance with your audio. No doubt I have shared my screen. I'm talking from here, right? We are doing online collaboration. We have all shared a Zoom link, right? We have done all these. But the challenge with respect to communication, would be your crystal clear audio. Right? Our audio is the bedrock of the meeting content. If I'm able to, right, if my audio is not good, you'll not appreciate what Biradar sir spoke sitting at Balki and was trying to convince you. If my audio is correct, probably few of you will be able to understand a few things and carry back a few things of applications of DSP. However, right, please remember your audio is against a lot of factors, right? There is degradation in clarity. We am talking now that I'm using echo canceller based sound system and I'm trying to talk to you. But what happens is in process, right? It's a through net, right? Your information, right? There can be a problem. There can be a problem of echo. There can be a problem of hiss. There can be volume fluctuations from person to person and also background noise. These are few problems, right? When you're attending a conference and we're having a meeting in a group, right? Through online mode, right? When you are transmitting audio, therefore, these will be the problems. What will be the problems? One is echo, is volume fluctuations, and background noise. And all these are all examples of problems that can contribute to a poor meeting experience, right? Therefore, if my audio is not clear, then he'll say, what is that? I was not able to hear him. His voice was not clear. Right? His pitch was not good. There was noise in the background. All this will be a problem. Therefore, even the highest quality video signal won't make up bad audio. Right? Even the best, right? I have stopped sharing my video. My camera is off now. But even the best video I sent, if audio is not correct, then it will be a problem. Right? It will irritate you. Right? When you are watching a match or something, if commentary, right? If the commentary is not heard, only can you just imagine of watching only video, right? No background commentary, and it will be a problem. You will not enjoy. Right, you have Sunil Gavaskar, Ravi Shastri, and others giving commentary, right, on the live cricket match between India and New Zealand. Probably he'll enjoy it. If audio is not good, then he'll have a problem. That's why it's important that every unified communication, right, space is equipped with right audio technology to ensure the clearest, most intelligible audio possible. Right? You are in the age of artificial intelligence. You are in the age of machine learning. You're talking of robotics. You're talking of data, right? Other things. You'll have to make this system, right? The audio that's transmitted, right? Using your DSP, right? Can we do this? Therefore, one example I've taken now, right? I have tried to show an image, right? You are sitting in a class, right? Therefore, what happens is your noise of your fan that's coming, right? It vibrates, right? Then too far from the speaker, right? What is that? Is the speaker who is there, who is standing far away from the microphone and is trying to talk to you, right? Far ahead from the, right? Your loudspeaker is aware, you are not able to do this. This will be a problem. Therefore, DSP is about making audio better, right? What is that? DSP is about making your audio better, removing unwanted noise and echoes that can be troublesome at the best and an absolute nightmare at the worst for achieving successful and productive online collaboration in terms of a meeting. Cutting out those problematic issues, whether it's hissing, reverberation, humming, or other noise, takes algorithmic manipulations that's highly specialized to address each of these particular problems. Therefore, you'll find a lot of applications, your DSP applications with respect to this. Then the most important part of this is your analog to digital conversion or digital to analog conversion. Most of your DSP systems have the capability of converting your analog signals into digital signals, right? The information that's being received from your microphones, it's being converted into its digital version. Right, some of your microphone systems will also supply a fully digitized signal processor, right? That's already ready for processing. If it's not there, probably you'll have to convert them and do it, right? At the other end, at the far end, right, your DSP converter will convert D to A and pass on this information in the form of an amplified signal, right? For A to D, right, analog to digital conversion, that is the analog mic signal to your digital signal to your voice. This is important in case of your transmissions. The next one, right, is with respect to your, right, when you're meeting with, meeting participants via audio endpoints such as phone, PCs, right? Typically, the DSP's first job is acoustic cancellation, right? The first challenge, right, the first thing which, right, any DSP system that's being inbuilt or that's being taken, right, that has to do this echo cancellation, right? You all understand this. What do I mean by echo? Acoustic echo cancellation basically prevents a person who is speaking from hearing the voice being played back on the other end as an echo and causing confusion. I'm talking to you all, right, students of 5th sem, right, TC, right, EC at Pandharpur, using a system. If my voice is echoing, most of you would say, right, sir, there is a problem, you would left the meeting, right? What do I mean by that is I'm able to hear my own voice. That same voice is coming. If I have 2 logins now, the computer which I've used to log in, or the laptop which I've used to log in, if I create 2 logins here and try to install this, and what happens is IMO might be generated. Therefore, it has to be addressed. This has to be addressed. Therefore, what is this is normally, right? You are a client, right? You're talking to client B. Therefore, voice of client A, right? What all he is speaking using a microphone, right? And then you have a loudspeaker. He's able to speak. But if at this point, if you are able to get back your signal, then it's a problem. Or when the client is talking back to you, right? If you are able to hear voice along with his voice, and also it's a problem. So what we do in this particular case is you have a client, right? Therefore, using a microphone, right? You are sending a signal, then you subject this particular signal to your AEC, Acoustic Cancellation algorithm. What happens is client B is able to, it doesn't have an echo problem, he is able to hear you. What happens is this information remotely passed on to the client. This is how you can have an effective communication. This is part and parcel of your audio processing, where you will find an application of your DSP. The next one is automatic gain control. What do I mean by this? Once echo is removed, right, DSP will provide you with automatic gain control. Right? What is this basically? DSP should be able to, this digital signal processor should be able to amplify each incoming signal from your microphone, and it should be able to brought to a same level. What happens is, right, if somebody is sitting very near, right, if his sound, right, is very high, and it might hamper the ears of a person, right? For example, someone who is 10 feet away from the microphone should be, right, should sound just as loud as someone who is sitting in front of it. Without AGC, users from far end might get blasted by a loud spoken person or strain the ears that he is using. What AGC does is it will adjust the volume of voices throughout the conversation to make and keep this conversation at a comfortable level. AGC can be tremendously beneficial for decreasing volume audio fatigue. What happens is, right, it irritates. If somebody is speaking very loudly, right, and if it's being passed on, it might irritate, right? Therefore, your automatic gain control will play a very important role in reducing this, right? Then this is an example, right? Where I have said, right, somebody is far away, the other one is this. Therefore, if you have AGC, then what happens is the conversation between these two people will be comfortable. Then mixing and gating. These are again important applications with respect to DSP, right? Mixing of your signals, right, and also gating of signals. And these are two very important applications when we have multiple people speaking or multiple systems working together, right? Right. Each example, right? Musicians especially, one is singing, the other fellow is on a violin, somebody is on tabla, somebody is on guitar, somebody is on some other musical instrument, right? When you're transmitting this information, you want all this information to be synchronously transmitted. Only then you'll enjoy, right, the singing and the background music that's being given. If there is a mismatch between the singer and the musicians who are playing on different instruments, and it will be a problem. But proper mixing has to take place, and proper gating has to be done so that which instrument is allowed, what instrument is allowed, when audio is only, when the singer is allowed, when only musicians are allowed, all these will be very important. Therefore, mixing and gating are important functions that control the microphones, right, that are actively transmitting, right, at the given time to a specific output. If all microphones have to be fed with one output, such as a telephone line or a video device, each microphone's input has to be added to the output signal. To do this, right, probably you'll have to convert all signals into your analog signals, mix them up. Then again, you'll have to separate them and ensure that information is being properly reconstructed and done. This is called mixing. What is that? If all the microphones are being fed with one output, right? Each microphone input has to be added to the output signal. This is called as mixing, and it defines which microphones send signals to which desired output. Right? Each might be connected one to one or many to one. It depends. Conversely, unmixed means every microphone has to be separate output. If you're bringing everything and mixing up and sending, or you're doing it individually, right? Each one is independent. The outgoing signals might be routed through multiple outputs simultaneously, or they might be doing internet, phone line, and local sound reinforcement amplifier, right? This can be a problem. Right. The next one is you have multiple inputs and output that's being mixing. This is what is being shown. Right? Any combination of wired and wireless microphones, right? Therefore, you have this is the aux input, right? That's being fed. This is your sound system which you are doing. Then you have conference system that's there. Then all these, in order to do this proper mixing and gating has to take place. Multiple input output setup for mixing and gating. Right? You have a sound system, you have a conference system, a network that teaches. Right? One end somebody is taking the other end. You have a network switch. All these combinations, right, would be that. Then gating means, right, you're literally sending one signal, or you're activating one, or you're deactivating one. That's what is the meaning of that particular one. Right? This is what it is. Then you might have two different speakers setting at two different points, and probably you'll have mix minus setup as an example, where sometimes you'll have to mix it up, sometimes you'll have to take it up. Right? This is how your DSP will play an important role. There are other applications also. There are a lot of other applications where we'll be talking of noise reduction. Sir, am I audible or it's all right? Hello?
Yes, sir.
Thank you, please. Somebody has to tell me because I'm at Balki. I do not know what's happening at Pandrup. Okay, thank you, please. However, other applications is you might have you need to have a signal processing algorithm that will reduce noise. As I said, whether it's an additive noise or a multiplicative noise, whether it's a Gaussian noise, what type of noise it is, based on that you'll have, right? Therefore, this includes noise reduction. Then it might be other things like, right, other intelligent capabilities, right? You'll have to have master mute, right, which quickly mutes everybody, volume control, right, which will control the volume of each, right? Probably you have this now, right? When we are using Zoom, probably all these capabilities are required, right? And your teacher would have, right, given me as a host, wherein I can control. I can allow somebody to talk, I cannot, right? I may not allow to do this, right? Therefore, these are important applications. Then coming to your telecommunication, I was being told by Dr. Matpati that this is also important. That is, you have applications in telecommunication. Application in audio is one, application in telecommunication, right? Your modern telecommunication system, right, will have normally we use narrowband signals. In such a case, right, you'll have narrowband interference. For this, you'll have to address them. Then you have radio frequency interference. These are signals that are complex in nature, and hence it will be natural for a complex DSP technique to be used to process them. Right? Normal DSP cannot be used in these particular cases. Right? Narrowband interference, then your RF interference. In these cases, because signal is not normal, it's a very complex signal. So complex DSP techniques are being used. I do not know. I will not get into this stuff to explain how different they are. Probably I'll lose the topic. right? Then your telecommunication, remember, right? Most of your telecommunication services, right, or your telecommunication systems, they'll require processing of information in real time. As you all are aware, right? You are aware that processing of information has to be done in real time. What do I mean by real time? The instant I'm talking, the instant I'm able to address you, you are able to hear it. Right? Therefore, most of your telecommunication systems, right? Take mobile and if your signal right is being delayed by certain time, then it's a problem. Right? You cannot have conversation. Therefore, processing in real time. In this particular case, you have to use adaptive complex filtering. Normally, you would have heard of, maybe in your class, you have heard of adaptive filtering. In our case, right, I'm talking of adaptive complex filtering. If time permits, I'll talk on this also. But remember, when you're talking of multiple communication channels, information has to be processed, right? Parallelism has to be there. Parallelism has to be there, right? Therefore, your parallel processing systems are indicated. Therefore, we'll have to take this. Then you probably you'll be studying regarding filter banks in your DSP. Therefore, adaptive complex filter banks are normally being used in your telecommunication. Right? It's one particular scheme where your MIMO systems, right? When you're talking of narrowband interference in MIMO systems, right? In these systems, MIMO, I mean multiple input, multiple output communication systems. In these cases, right, you'll be using adaptive complex filter banks. The next one is, right, I got a very, very important example, right, where really I have worked and I have a bit of experience in working with these, right? The Doppler ultrasound, right? The ultrasound, right, that you take, right? Maybe ultrasound of your kidney, ultrasound of your liver. These days, right, since, right, at very young age, we are being told people are having problems of heart attacks, right? Heart stroke, brain stroke, all these are there, right? Therefore, one important is your ultrasound system, right? And remember, these ultrasound systems, they work on Doppler concept, right? The Doppler concept, right? For your Doppler ultrasound, right? Normally what it does is, it's going to, there are two things here I should make clear before I speak. One is you're able to visualize, right? You are able to take a spectrum of that and that spectrum is being displayed. The other one is when for example, I'm taking ultrasound of heart. That's called as echocardiography. This is being done in terms of ECG, right? What is that? Then there are other modes. Continuous wave Doppler, pulse wave Doppler, and the other things. B-mode images, color Doppler. There are multiple one. But this is not just, right, your heart is a dynamic one, right? It's a dynamic one. It's continuously beating. So what in this particular case is, along with your image, your audio has to be recorded, right? Your Doppler, it's able to record and do the spectrum reconstruction happens correctly. But the baseline of your audio that's there, it's not able to fix. For the DSP has to play an important role. Therefore, the Doppler ultrasound system has a spectrum display that indicates blood flow direction, right? If it is towards, right, what normally we do is we place, I'll switch on my video and try to display it to you. Right? For example, you're all able to see my hand, I suppose. Okay, just a minute, please. Just my audio. There was, for example, this is just, right, heart is size of your fist, right? I'm interested in diagnosing, right? There is some problem with my heart. Therefore, what I do is I place a probe. I place a probe on my chest. Remember, this is being done in multiple ways. One is at the bottom of your heart, one at the top of the heart, and two at the rib cages. Therefore, we call them by different names. We call them as, right, suprasternal, right? Then you have subcostal, then you have apical, then you have parasternal. I'll not get into all this stuff. Only point I'm saying is, when you're placing a probe on your chest, right? Hope everyone is able to see my video. My hand is clear. I'll stand up and show, right? Example, I'm taking this pen as a probe, right? I'm placing it on my chest. Then the blood that is flowing towards your transducer, right? That's in the direction of your transducer. That's normally red. The one that's moving away from your transducer, that's blue, right? These two, the spectrum of this is being, right? I'll show you a image here, probably that should be clear, right? Just a minute, right? Okay, right? Now you see what happens, right? This is an ultrasound. What you have done now is, right, we are interested in, all of you look at this very carefully. There is very important application of this, right? And lots of research possibilities are also there. Now what we have done is, right, this is the image. This is one you have done. On this, using a blue line, they are able to mark the spectrum. They are able to mark the spectrum, right? They convey different information. They convey different. This is a transducer, right? This is your one, right? Then this particular line is showing, right, the direction in which whether your blood is flowing in the forward direction or reverse direction. This is one, right? But I haven't shown you an audio signal. This normally is also accompanied by an audio signal, right? The upper is, right, the upper is a tomography image. The bottom is your spectrum image. You're using Doppler. This is what it is. What does it do, right? You have a probe, right? Then you receive your signal. This received signal is being sampled 1 by Fs. And what you do is you do an envelope detection. You do envelope detection. Then you construct a B mode image. It's basically a black and white image, which gives you, right, an image, right, a brightness image. B normally stands for brightness. This is what it is. The other part is your phase detection, where you're detecting the Doppler spectrum. This is what it is, right? What you have done, right? You're talking of what is at what different points. At R1, for example, I placed a probe, right, at R1, right? This is your signal. At R2, this is the waveform you're getting. At R3, this is the waveform you're getting. And you're analyzing this. Therefore, what happens is your PQR analysis. Your ECG basically has a PQR arrangement. And inverted U will represent a stenosis. Right? I'll not get into the pearl. I do not know how many of you will appreciate and understand this, right? But example is of an ultrasound. What is that? You're taking a probe, you're receiving your signal, you're developing, you're able to develop its, you are able to reconstruct its envelope, and you're able to construct an image. Similarly, you're able to do its spectrum. The problem now, right, is, right, when you're doing, right, I said Fs is there in this particular one. I'm sampling at a rate of 1 by Fs, I said. Because Fs is my sampling. So this is what it is. If you are talking of a power and your signal, right, the spectrum will be between Fs by 2 minus Fs by 2. This is what it is. But what happens is when a clutter is being introduced, right, you have a clutter, then there is a shift in your Doppler. There is a shift in your Doppler, and therefore it becomes a problem, right? Then you will not be able to do this. Then the other thing is, if this Fs is not being maintained, what happens is one will overlap with the other. So what you're doing is, you're taking two signals now. One is your Doppler, the other one is clutter. Then you're analyzing in the form of I and Q signals. So what is being done, right? You have a signal, right? You have a B mode, then you display it. Then what we do is we go for the same signal, we go for quadrature detection. Then you do a high pass filtering. Then the spectrum of that particular image is taken and that's being displayed. But the problem lies with the third line now. The problem is there is a baseline for this using which, right, for both image and spectrum, I can move around and I can do it. Problem is with respect to your audio, which will not have a baseline. It will not have a baseline. Therefore, it will be a problem. This will be a problem. Therefore, what is the problem? Right? For example, hope everybody is able to see these images. Right? I marked. This is the spectrum. This is the spectrum. What I've done is I've taken a spectrum of an image. This is your baseline. I marked the baseline. At instant A, if you look in, right, there is what is that? Your top of your signal, right? The maximum of your signal, right, is being cut it off, right? It has been cut, right? Therefore, you are not able to analyze. Therefore, what happens then? What I have done in this particular case, A is this. Therefore, this is your baseline, plus 0.5, minus 0.5. I've done this, right? Therefore, if you look in this, what I do is change the baseline. Change the baseline. And what happens is, changing the baseline, I'm able to bring down the amplitude level and measure it. But this doesn't happen with your signal. This is possible with this. Therefore, this is right. What you have done is, because of aliasing, the maximum of your signal was cut off at instant A, and it was displayed at the bottom. I repeat, it's important. All of you listen to me carefully, please, and watch at the screen. This is a signal I have taken. You can all observe. You can all see that the top of the portion has come down. This is being displayed here. Therefore, because of aliasing, at instant A, aliasing has occurred. What do I mean by aliasing is, your higher frequency component are overlapping with your low frequency component. Therefore, there is an overlap, since your FS was not properly taken. But what is there in your these ultrasound systems is, there is a provision with respect to correcting these aliasing process by changing the baseline. You'll able to overcome the problem of aliasing in case of ultrasound images. But at this particular point, you can see maxima are able to see, and you are able to overcome the problem. The same would not be possible. The same will not be possible for your signals. Now, this is in terms of, you have this, right? You can see, right? One is with zero base shift. What is happening is, this is your display area. Part of your signal is being cut off. You are shifting it. If you are shifting this, if your baseline is being shifted by this, you are able to see both of them. One is in forward direction, the other one is in the reverse direction. You are able to see this, and you are able to correct. I repeat once again, this is a very important example. I'm taking the example of ultrasound where your spectrum and your audio signals are simultaneously being processed. For connecting your spectrum, have a provision with respect to baseline. You can see in your image A, right, or point A, right? With zero base shift.
Excuse me, sir.
Yes, please.
Hello.
Yeah. Yes, please.
Hello. Excuse me, sir.
Yeah, please tell me.
Sir, your voice is breaking, sir. Your voice is breaking, sir.
Okay. Really,
Yeah, sir. Your voice is breaking, sir.
Okay, I'll see what happens. It's all right now?
Hello.
Are you able to hear me? Hello?
Hello, sir. Your
Madam,
voice is breaking,
sir. Are you able to hear me?
No, sir. Your voice is breaking, sir. I'm not able to hear properly, sir.
Yeah. Just a second. There would be a problem with the connector which I have connected.
Yes, sir.
Okay, thank you. I have connected with the based system. Really, I touched with my leg and it has gone. Okay, fine. Sorry. Right. Therefore, what happens now is, should I repeat? Madam, should I repeat?
No, sir. It's okay, sir. You can continue.
Okay. Anyhow, right? At point A, because of aliasing, the maxima at which it has occurred, right? It was being chopped off. You have the right portion being cut. Therefore, you can play with the baseline, which is there with the system. Your other things, it's not there. What we do is, right? We use this DSP systems where these lines can be fixed so that your these spectrums can be reconstructed back properly. This is what it is, right? You have two baselines. There is a shift, you can see. But if you look into the spectrum, it's a continuous spectrum which we can analyze both forward direction and the reverse direction, right? It's important to note is, right, systems, right, are being inbuilt with baseline adjustment, which helps in adjusting the aliasing problem. With respect spectrum, we'll have to introduce one more, right? Therefore, what's being done is basically we are analyzing I and Q signals of carotid artery, right? We are using a string pattern that's basically Mark IV Doppler pattern that's being J. Johnson and Johnson company. And they have done the machine that's being used is of Toshiba for generating and collecting these information. This is what it is, right? This is what I had, right? I stop, right? If you have any questions, right, I'll be more than happy to take them. Stopping because I have. If I go to other application, I'll take 1 more hour. I'll not get into that. Any questions, please now?
Students, if you have any questions, kindly ask. Students, kindly ask some questions if you have any query.
See, it's not possible for me to talk of all applications of DSP in 1 hour class. Right? Probably, I do not know. Probably each application will need a lot of time. But anyway, if there are any questions, I'll be more than happy to answer.
Yeah, so I'll ask Komal. Komal Thodat, can you please ask some questions if you have any query?
No, ma'am, no lot of.
Okay.
Okay.
Very much thank you for your session. Is really very nice. I am very much find it very much interesting. So we reach with the last point of this session, that is vote of thanks. So first of all, good afternoon, everyone. It's my privilege to propose a vote of thanks. I would like to thank Dr. N.M. Virada sir for enlightening us with his vast knowledge and experience. It gave deep insights into the subject of DSP. Also, I would like to thank sir for accepting our invitation from his busy schedule and guide our students. Last but not the least, I would like to thank our students for be attentive. So thank you so much, sir. Thank you so much, sir.
Thank you. It was a pleasure talking to you. Right? Probably I do not know. Probably there would be audio problems always. I do not know.
Yeah, no, yeah. So it's happening so students kindly fill some feedback in the chat box. Fill some feedback in the chat box.
It's all right, ma'am. I'll take a leave. I'm supposed to move to a meeting also. Right. I thank you, madam, for the wonderful words. And
yeah, so thank you so much.
Please convey my thanks to Madpati sir, Power madam,
yeah,
and others also, please.
Of course, sir. Of course, sir. I'll say, sir. Thank you so much, sir, for your kind words, sir. Okay, sir.
All the best to all the students. All the best to all the students. If they have something, we'll look.
Thank you, sir.
Right.
Have a good day. Have a good day, sir.
Thank you, ma'am.
Students kindly fills that feedback in the chat box is very much important. It was expected that you're supposed to ask some questions because a very eminent personality was there, and you should ask some questions because it will feel like कि आपको समझ में आया नहीं आया. Still you have not asked, so at least you must fill the feedback at least. Okay. So from next time, at least you must ask some questions It was expected.